have learned that when the emitter terminal of a transistor is common to the input and the output, the transistor is said to be in common emitter configuration. For a transistor in common emitter configuration, the forward-biased emitter-base junction forms the input circuit, where the input voltage is VBB, while the reverse-biased collector-emitter junction forms the output circuit, where the output voltage is VCE. We shall try to understand the operation of the transistor as a switch by analyzing the behavior of the base-biased NPN transistor in the common emitter configuration. On applying Kirchhoff's voltage rule to the input of the circuit, we get VBB is equal to IB into RB plus VBE. Let this be equation 1. And on applying Kirchhoff's voltage rule to the output of the circuit, we get VCE is equal to VCC minus IC into RC. Let this be equation 2. Here the input voltage VBB is represented with VI and the output voltage VCE is represented with VO. Then the equation 1 can be written as VI is equal to IB into RB plus VBE. Let this be equation 3. And the equation 2 can be written as VO is equal to VCC minus IC into RC. Let this be equation 4. Let us now discuss the change in the output voltage VO with a change in the input voltage VI. In case of a silicon transistor, the cutoff voltage is 0.6 volts. As long as the input voltage VI is less than 0.6 volts, the transistor is in the cutoff state and the collector current IC is 0. Then from equation 4, the output voltage VO is equal to VCC. When the input voltage VI becomes greater than 0.6 volts, the transistor goes into the active state. In the active state of the transistor, the collector current IC increases linearly with increase in input voltage VI. Then, the output voltage VO is equal to VCC minus IC into RC. The output voltage VO decreases linearly till its value becomes less than 1 volt. Beyond this, the transistor goes into the saturation state. That is, with further increase in input voltage VI, the output voltage further decreases to 0 but never becomes 0. In the saturation state of the transistor, the collector current IC is maximum. Let us now discuss about the transistor as a switch. When the input voltage VI is low, the transistor is in the cutoff region. In the cutoff region, the collector current IC is 0 and it is not conducting. Then it is said to be switched off. If the input voltage VI is high enough to drive the transistor into saturation state, the output is low and very near to 0, and the collector current IC is maximum. Then it is said to be switched on. Let us now discuss about the transistor as an amplifier. To discuss the transistor as an amplifier, we use the active state of the transistor. in the active region of the transistor, the output voltage, VO, decreases linearly with an increase in the input voltage, Vi. If delta Vi and delta Vo are the small changes in the input voltage and the output voltage, then the ratio of the change in output voltage to the change in input voltage is called small signal voltage gain. That is, AV is equal to delta VO by delta Vi. Let this be equation 5. When the input voltage Vi is at the midpoint of the active region, then the circuit behaves as a common emitter amplifier with voltage gain AV. This voltage gain AV can be expressed in terms of the resistances in the circuit and the current gain of the transistor. We know that the current gain of the transistor, beta AC, is equal to delta IC by delta IB. Let this be equation 6. From equation 4, we can write the small change in output voltage, delta VO, is equal to 0 minus RC into delta IC, which is equal to minus RC into delta IC. Let this be equation 7. Similarly, from equation 3, the small change in voltage delta Vi is equal to RB into delta IB plus delta VBE. But delta VBE is negligibly small in the circuit. Then delta Vi is equal to RB into delta IB. Let this be equation 8. On substituting equations 7 and 8 in equation 5, we get AV is equal to minus RC into delta IC by RB into delta IB. Let this be equation 9. On substituting equation 6 in equation 9, we get the voltage gain of the amplifier as AV is equal to minus beta AC into RC by RB. Thus, the transistor in the active region can be used as an amplifier. You have learnt that when a transistor is in the active state, a small increase in the base current IB causes a large corresponding increase in the collector current IC. Thus, a transistor in the active state behaves like an amplifier. The operating point of a transistor as an amplifier is fixed somewhere in the middle of the active region. We know that the current amplification factor, beta AC, is equal to beta DC. That is equal to delta IC by delta IB. Let this be equation 1. And the voltage gain AV is equal to delta VO by delta VI. Let this be equation 2. These expressions are applicable to the transistor as an amplifier of DC voltage. Now let us look at the transistor as an amplifier of AC voltage. An AC sinusoidal wave representing input voltage Vi superimposes over the supply voltage VBB for the base emitter circuit. The input AC voltage Vi causes sinusoidal variations in the base current IB. The sinusoidal variations in the base current IB introduce corresponding sinusoidal variations in the collector current IC. The sinusoidal variations in collector current IC produces corresponding changes in the output voltage VO, which can be measured across the battery VCC and the resistance RC. Large capacitors are used to block the DC voltages while measuring the AC variations across the input and output terminals. Let us now derive an expression for AC voltage gain in the transistor amplifier. Initially, let us assume the input voltage Vi is equal to 0, and applying the Kirchhoff's law to the output part of the circuit, we get VCC is equal to VCE plus IC into RC. Let this be equation 3. Similarly, applying the Kirchhoff's law to the input part of the circuit, we get VBB is equal to VBE plus IB into RB. Let this be equation 4. When the input AC voltage Vi is not 0, we get the sum of Vi and VBB as VBE plus IB into RB plus delta IB into RB plus RI. Let this be equation 5, where Ri in equation 5 is the internal resistance of the input circuit, which is equal to delta VBE by delta IB. From equations 4 and 5, we can write the input voltage Vi is equal to delta IB into RB plus RI. The input voltage Vi can be written as Vi is equal to delta IB into R. Let this be equation 6, where R is equal to RB plus RI. On rearranging equation 3 for the output circuit, we get VCE is equal to VCC minus IC into RC. Let this be equation 7. Thus, a small change in VCE, delta VCE is equal to delta VCC minus delta IC into RC. Let this be equation 8. Since VCC is fixed, delta VCC is equal to 0. Thus, a small change in VCE is given as minus delta IC into RC. The change in VCE is equal to output voltage VO. Then, VO is equal to minus delta IC into RC. Let this be equation 9. The AC voltage gain AV is the ratio of output voltage VO to the input voltage Vi. Substituting the values of Vi and VO from equations 6 and 9 in the equation for AC voltage gain, we get AV is equal to minus delta IC into RC by delta IB into R. Let this be equation 10. We know that the current amplification factor beta AC is equal to delta IC by delta IB. On substituting the current amplification factor in equation 10, we get the AC voltage gain AV is equal to minus beta AC into RC by R. Let this be equation 11. Then the AC power gain in a transistor amplifier is equal to the product of the current amplification factor and voltage gain. That is, AP is equal to beta AC into AV. Note that a transistor does not generate power. It just uses the power from the batteries in its input and output circuits to amplify an AC signal. An oscillator is an electronic device that converts DC voltage into AC voltage. An oscillator consists of a transistor amplifier and a feedback network that extracts a part of the output of the amplifier and feeds it back as input to the transistor amplifier. A commonly used feedback network consists of an LC circuit formed by the combination of an inductor with inductance L and a capacitor with capacitance C. This is a resonant circuit that produces an output of a particular resonant frequency. A simple circuit used to understand a transistor oscillator is shown here. The circuit contains an NPN transistor in the common emitter configuration, with the base emitter junction forward biased and the base collector junction reverse biased. The input circuit of the transistor is connected to a coil T1 across terminals 1 and 2. The output circuit of the transistor is connected to a coil T2 across terminals 3 and 4. Note that coil T2 forms a part of the LC circuit used for the feedback network. Coils T1 and T2 are wound on the same core so that they can influence current in each other through inductance. The output circuit also contains a switch S. When the switch is open, the transistor cannot conduct and is in the cutoff state. When the switch S is closed, the collector current rises from 0 to a peak value as shown in the graph. As the collector current rises in coil T2, it induces a current in coil T1. Due to this inductance or positive feedback from coil T2 to coil T1, the emitter current also rises to a peak value as shown in the graph. When the inductor current reaches the peak or becomes maximum, it stops rising further and the transistor goes into the saturation state. When the transistor goes into the saturation state, the current stops changing in coil T2 and therefore inductance or feedback from coil T2 to coil T1 stops. When the inductance or feedback from coil T2 to coil T1 stops, emitter current starts decreasing. As the emitter current decreases, the collector current also starts decreasing. The decreasing collector current in coil T2 sends a negative feedback through induction to coil T1. The negative feedback further decreases the emitter current and the collector current till both become 0. At this stage, the transistor is back to the cutoff state. From the cutoff state, the transistor moves to saturation state and back. The cycle continues, giving rise to an AC output. The frequency of the AC output voltage is equal to the resonant frequency of the LC circuit formed by the inductance L of coil T2 and the capacitance C. Since the LC circuit is connected on the collector side of the common terminal, this form of an oscillator circuit is called the tuned collector oscillator. You have already learned that when the P side of a PN junction diode is connected to the positive terminal of a battery and the N side is connected to its negative terminal, the diode is said to be forward biased. And when the P side of a PN junction diode is connected to the negative terminal and the N side is connected to the positive terminal, the diode is said to be reverse biased. You have also learned that a diode allows free flow of electric current under forward bias, but allows little or no current to flow under reverse bias. This property allows a diode to work as a rectifier. A rectifier is a device that converts alternating current into direct current. Now, let us consider a circuit in which an AC input is connected to the primary coil of a step-down transformer. A diode is connected in series with a load resistance R across the ends S1 and S2 of the secondary coil of the transformer as shown. Due to the AC input, S1 is positive and S2 is negative for the positive half cycle, while in the negative half cycle, S1 is negative and S2 is positive. Thus, the direction of voltage applied across the diode keeps changing. When S1 is positive and S2 is negative, the diode is forward biased and allows current to flow through it. Thus, during the positive half cycle, current flows through the load resistance and we get a voltage output across R as shown. When S1 is negative and S2 is positive, the diode is reverse biased and allows negligible current to flow through it. This current is so small that it is considered to be equal to zero. Thus, during the negative half cycle, no current flows through the load resistance and we do not get any voltage output across R. Here, the diode produces a pulsating voltage across the load resistance R. Since the output voltage is only in one direction, it is called rectified output. Since this circuit produces rectified output only for the positive half cycle of the AC wave, it is called a half-wave rectifier. Now consider the circuit as shown, in which an AC input is connected to the primary coil of a step-down transformer. The ends S1 and S2 of the secondary coil are connected to the P sides of two diodes whose end sides are connected to each other. The load resistance R is connected across the end sides of the two diodes and the center tap C is provided at the middle of the secondary coil. The potential at S1 and S2 changes with the AC input cycle. When S1 is positive and S2 is negative, diode 1 is forward biased and allows current to flow through it. However, at the same time, diode 2 is reversed biased and does not allow current to flow through it. Thus, during the positive half cycle, current flows through the load resistance R via diode 1 and the center tap C, and we receive a voltage output across R. When S1 is negative and S2 is positive, diode 1 is reversed biased and does not allow any current to flow through it. However, at the same time, diode 2 is forward biased and allows current to flow through it. Thus, during the negative half cycle, current flows through the load resistance R via diode 2 and center tap C, and we receive a voltage output across R. Thus, a combination of the two diodes produces more continuous pulses of rectified voltage across the load resistance R. Since this circuit produces rectified output for both the positive and the negative half cycles of the AC wave, it is called a full-wave rectifier. Although the output of a full-wave rectifier is more continuous than a half-wave rectifier, it is still in the form of unsteady pulses of voltage. A more steady output can be received from a rectifier by connecting a suitable capacitor in parallel with the load resistance. The capacitor prevents the voltage from falling sharply through the load and provides a more steady output as shown.